The normal distribution is the most widely known and the most widely used of all statistical distributions. This is because it fits so many natural phenomena and human characteristics such as weight, height, life expectancy for human beings, and so on. It's also the suitable distribution for so many economic and business variables such as cost and income. And because of its many applications in various fields, it is maybe the most important distribution of all. We sometimes refer to the normal distribution as the Gaussian distribution. This is in reference to Carl Gauss, the statistician who introduced this distribution. The normal distribution has some main characteristics or properties. These are, first, that it's a continuous distribution, or it's a distribution for a continuous random variable. It is symmetric about the mean, and by symmetric about the mean, we mean that looking at this curve over here, the mean is this vertical line in the middle, so the right hand side of the curve is just a mirror image of the left hand side, so we say that it is symmetric about the mean. It is bell-shaped. We call this shape a bell-shaped because it resembles the shape of a bell. It is unimodal, meaning that it has only one peak, one mode, and it is asymptotic to the horizontal axis, which means that it approaches the x-axis from the right and the left sides. It doesn't really touch the x-axis, but it becomes very, very close as it approaches infinity. And the total area under the whole curve from negative infinity up to infinity has to be 1. As in any other probability density function. Finally, we say that the normal distribution is a family of curves, meaning that we can have an infinite number of the bell-shaped distributions like this one, and they are all normal, but they can be flatter or with a higher peak, and they can have different means. So we will have a look at different normal curves in a while. The probability density function of a normal random variable takes this complicated formula that you can see over here. We can see that f of x is, it depends on some parameters, like pi, which is a constant. Pi is the 3.14, which you can get from your calculator. But then we can also see in the formula that there is mu, which is the mean, and sigma, it appears twice, which is the standard deviation of the distribution. And then there is E, which is the 2.718, the natural exponent. So we have E and pi, these are constants, but then mu and sigma, it depends on the distribution of the variable itself. And we have x, which is the variable, which in this case, as we mentioned, it takes values from negative infinity up to infinity, not like the uniform, which is limited between two values a and b. You do not have to study this formula by heart. You will not evaluate it or use it in this course. But we need to know what are the main parameters of the distribution, which we can see from here. These are mu and sigma, because anything else is either constant or the variable itself. Okay, so we just mentioned that we have an infinite number of normal distributions, and these differ from each other according to the two parameters that we have just seen in the formula. These are mu and sigma, the mean and the standard deviation. So now let's look at the effect of changing the mean and changing the standard deviation. What will happen to the distribution, the normal distribution? Let's first look at changing the mean. We know that the mean is in the middle of the distribution. So if we look at the first curve, the black one over here, it has a mean equal 0, I guess. So if we change this mean and we look at another normal distribution that has mean equal 1 or 0.8, I guess, something here. So the whole distribution will look exactly the same, but it will be shifted to the right. Again, if we change to the green curve, the third distribution here, the mu is 2. So again, it looks exactly the same as the previous two, but now it has a mean equal to 2, so it has shifted again to the right. The black one is mu 0, the blue is mu equal 1, and the green one is mu equal 2. So changing the mean shifts the curve to the right, but it keeps the same shape exactly. Now let's see what happens if we change the standard deviation. Again, look at the black curve over here. This is a normal distribution with a standard deviation equal 1. So what happens if we use a standard deviation that's equal half? If we decrease the standard deviation, this will give us a normal distribution located at the same mean. We have the same mean 0, okay, but now it has a higher peak. What if we use a larger standard deviation? So the green one, the green curve, is a normal curve where sigma is equal to 3. So increasing the standard deviation flattens the curve. It gives us a flatter curve. So the smaller the sigma, the narrower the curve. The larger the sigma, the flatter the curve. So we can see that these three distributions, they all share the same mean, which is 0, but then they have different shapes according to their standard deviations. So the mean affects the location of the distribution. Let's say changing the mean shifts the distribution, while changing the standard deviation will change the shape of the distribution. In order to calculate the probability that a normal random variable falls between two values, what we have to do is to find the area under the curve between these two values. The problem is it's a curve, not a simple line as in the uniform case. So finding the area is not really straightforward. It doesn't have a simple formula like base times height or things like that. And the function itself is calculated as we is complicated as we have seen. So actually trying to find this area will need some complicated integrations, which we will not do. Luckily, we have a table that has calculated those areas or those probabilities. We have agreed that the area is equivalent to the probability. So we have a table that we will look at shortly that has calculated those areas and put them down in one page. But the thing is, we have just mentioned that we have an infinite number of normal distributions depending on different means and standard deviations. So in theory, we need to have one table for each of those distributions. So this doesn't seem to be logical, because then we need an infinite number of normal distributions to correspond to all different combinations of mean and standard deviations that we can meet. Like we'll have a table for mean mu equal 2 and sigma equal 1, and then mu equals 2.3 and sigma is 1.5, and so on. Luckily, we do not have to do this because this is not applicable. We have a process that we call standardization of normal random variables that we can apply to any normal random variable, and it becomes what we call a standard normal random variable. And that's why we have only one table, which is the table for the standard normal random variable. If the variable we are interested in is the standard normal, then we can use the table directly. But if the variable is not standard, we will standardize it and then use the standard normal table. We will now look at the properties of a standard normal distribution. The standard normal distribution is a normal distribution that has a mean equal to 0 and standard deviation equal 1. And it looks like this curve over here. The center is 0 and sigma is 1. So if we substitute by 0 and 1 in f of x for the normal distribution, we will find that it becomes simpler. But anyways, we said that we are not going to use this formula anyways. The standardization process is converting any normal random variable with mean in general mu and standard deviation sigma into this standard normal distribution. Why do we do this? We do this because then we can use the standard normal table that we will introduce. So how do we standardize a normal random variable? Actually, this is the formula that we use for any normal random variable, say x, that has mean mu and standard deviation sigma. It becomes a standard normal random variable, and we denote it by z. By subtracting the mean and dividing by the standard deviation. So x minus mu over sigma, this gives us z, which we call the z-score, and we have actually talked about the z-score in the previous course, S101. So this is how we obtain it. Looking at this z-score, we can say that it gives the number of standard deviations, the number of sigmas, that the value x falls above or below the mean. So how far is x from mu? Let's say if x is here, how far is x from mu in terms of sigma? This is the meaning of the z-score. After standardizing, if the blue curve here is the normal curve for the curve for the normal variable whose mean is mu, let's say 3, and sigma is, let's say, 2. After standardizing, it becomes the standard normal with mean 0 because we have subtracted mu, and sigma equal 1 because we have divided by the sigma over here. So again, what we have done by the standardization is that we have shifted the mean from its place mu to become 0 over here by subtracting mu. And we have flattened or narrowed the curve whose standard deviation is sigma by dividing by the standard deviation over here, so we get that the sigma becomes equal to 1. So we change the location of the curve by subtracting mu, and we change the shape of the curve by dividing by sigma, and after doing this we obtain the standard normal distribution, which has mean 0 and standard deviation equal to 1. This process is called the standardization. We obtain the z-score, and then we can use the standard normal table to find areas or probabilities without having to evaluate the complicated function that we have seen. Now, after we have obtained the z-score, so we have a standard normal random variable. Let's get introduced to the table, which is table A.5 in your textbook. How does it look like and how can we use it? The standard normal table gives the area under the standard normal curve between 0, which is the mean, and some other point, different values that we refer to as z on the positive z-axis. So it only gives areas between 0 and a positive value. So what if we want to find the area between 0 and a negative value? In that case, we use the symmetric, the point that the distribution is symmetric, which is one of the main features of the normal distribution. And then we get the area between 0 and z and say that it has to be exactly the same as the area between 0 and negative z. And we will look at many examples on that. The table lists the probability, as we said, between 0 and some value, positive value z. And let's have a look at the table now to see how we can read it. This is our standard normal table. We can see that on top of this table we have the standard normal curve and we have an area shaded under the curve between 0 and some positive value z. The z values are given from the margins of this table, and the areas or the corresponding areas or probabilities are given in the body of the table itself. The rows have the whole number and the first number, the first decimal place, and then the columns give the second decimal place. What does that mean? Suppose we want to find the area from 0 up to 1.45, for example. So we come in the rows and look for 1.4 and then move along to get, this is 1.40, 1.41, 1.42, 1.43, 0.44, 1.45. 1.4 comes from the row, 0.05 comes from the column, and the corresponding area or probability, as we can see, is 0.4265. So this is the area from 0 up to 1.45. We can notice that the area gets bigger as the z value is larger, which makes sense. The area from 0, let's say, to 1 must be smaller than the area from 0 to 1.2, and then if you move along, as z gets bigger, the area gets bigger as well. It approaches at 3.4, as we can see here, it's 0.4997, and then at 3.5 it's 0.49998, and so, and 6 it's 0.499999, so it's almost 0.5. Basically, it gets very close to 0.5 when you get to 3. Okay? The area from 0 to infinity is actually 0.5, because we know that the total area under the curve is 1 and that the curve is symmetric. So from 0 to infinity the area is half, and from 0 to negative infinity the area is also half. Again, this slide shows us the standardized normal distribution, and that it gives us the area or the probability from 0 up to a positive value z node. This is a closer look at the table because the previous one was too small. So again, the rows, as we can see, give us the whole number and the first decimal place, while the columns give us the second decimal place in z. And these values in the middle of the table, in the body of the table, these are the corresponding areas or probabilities. So as we will see on the next slide, if we want to find the probability that z is between 0 and 1.52, for example, we come in the rows and find 1.5, which is not here, but it's in the detailed table, and then move along the row until we reach 2.02. So the corresponding value, we can find it from the intersection of the row 1.5 and the column 0.02. Looking back at the table, we can find this probability to be 0.4357. So this is the area from 0 to 1.52. Please try to find it yourself to make sure that you can use the table correctly. Okay, what about if we want to find the probability that z is between 0 and negative 1.52, greater than negative 1. The probability that z is between negative 1.52 and 0, let me draw the curve, excuse my curve, but let's say that this is the standard normal curve and this is 0, the mean, and what we actually want to find is the area from 0 to, let's say that this is negative 1.52. So we want to find this shaded area over here. The point is, if we go to the table, we will not find any negative values. What we can do is we can say that by symmetry, the area from 0 up to negative 1.52 is the same as the area from 0 to 1.52, which we have just found, and we use the symmetry characteristic to find this probability. So in that case, the probability is exactly the same as the one we have just found. What if we want to find the probability that the standard normal random variable z is greater than some value? Can we do this? Yes, we can. We know that the table only gives the area from 0 up to a certain value. So if we want to find, let's say, the probability that z is greater than 1.52, what do we do then? We know that we can find the area from 0 up to 1.52, which we have just found to be 0.4357. And we also know that the area from 0 up to infinity is 0.5. So what we have to do is to subtract 0.5 minus 0.4357, and then we get the shaded red area over here from 1.52 up to infinity. So this is the probability that z is greater than 1.52. And again, by symmetry, we can find that the probability that z is less than negative 1.52 is exactly the same as the probability that z is greater than positive 1.52, which is again 0.0643. We can also find the probability that z lies between two values. For example, let's look at this probability here, probability that z is greater than negative 1.3 and less than 2.1. On the curve, it's this shaded red area over here. What we have to do is to know how to use our table. We know what the table gives us. We know some features of the distribution, the symmetry, that the total area is 1, that half of the area is 0.5. So what we can do is to split this probability into two parts. First, the probability that z is between 0 and 2.1, and this can be found directly from the table. Go to the row with 2.1 and then the column 0.00, and we'll find that the corresponding probability is 0.4821. But this is just this part here on the right. We have to add this to the probability that z is between 0 and negative 1.3. So probability that z is greater than negative 1.3 and less than 0. Again, by symmetry, this is exactly the same as the area from 0 to positive 1.3. Go to the table, go to the row that has 1.3 and the column 0.00, which is the first column. So the area is 0.4032. Adding up these two areas, 0.4032 and 0.4821, we get the probability that Z is between -1.3 and +2.1, and this total probability or total area is 0.8853. Now we look at a different case. Here we want to find the probability that Z, the standard normal random variable Z, is less than a certain value, a certain positive value. Let's say in this example it's 0.56. We want to find the probability that Z is less than 0.56. Again, we will have to split this probability into two parts. These two parts are the area from -infinity up to 0, which is known to be half because the total area under the curve is 1, and this is half of it, so that's 0.5, plus the area from 0 to 0.56, which we can check it from the table. We will go to the row 0.5 and the column 0.06. Look at the corresponding probability. You will find it to be 0.2123. Add it to 0.5, so we get the final probability, or the final area is 0.7123. Again, by symmetry, if we want to find the probability that Z is greater than -0.56, it will turn out to be exactly the same probability as this one, 0.7123, and I'm going to show it to you on the next slide. Let me try to draw the standard normal curve over here. So this is the center, 0, and the area we want to find is from some negative value, -0.56, up to infinity. So basically the area, the probability that Z is greater than this negative value. Of course, a negative value has to be on the left hand side of of the mean, because the mean is 0. So this is the area we need to find. Again, by symmetry, we will say that the probability that Z is greater than this negative value is the same as the probability that Z is smaller than the corresponding positive value, which we have seen on the previous slide. So it's exactly. Another case is, what if we want to find the probability that the standard normal random variable lies between two positive values of Z? So for example, we want to find the probability that Z is between 0.38 and 1.52. My advice is always to draw the distribution. It helps a lot to find the probabilities. So I'll try to draw the curve over here, and this is the 0, the center. What we want to find is the area between 0.38 and 1.52. So it's this shaded area over here, the one I'm shading at this moment. Okay, how can we find this area? We can actually find the area from 0 to 1.52 minus the area from 0 to 0.38. So the first one, go look it up. We found it before. It's 0.4357 minus from 0 to 0.38. Look it up. It's 0.148. So you get the area 0.2877. And remember always to draw. An important reminder here is that the standard normal random variable, or any normal random variable, is a continuous random variable. So the probability, as we said at the beginning of this chapter, the probability that this variable Z is equal to any value is 0. So the probability, let's say that Z equals 1.2, that's equal 0. That it's equal 2.4 is 0. Okay, so the probability that Z equal any value is 0, and consequently the probability that z is greater than a certain value is the same as the probability that z is greater than or equal to this value. So whether we put an equal sign or not, it doesn't really make any difference.